Swayam Prabha. Digital India. Educated India.
It does. Okay. So it's quite surprising, right? Yet interesting what batch TD0 converges to. So we have our data set of 5 episodes. Let us ask the following question. Which MDP has the highest likelihood of having generated these 5 episodes of data? Okay, we know that the MDPs we're looking at, right, have so many states, so many actions, this particular policy is being followed, the discount factor is fixed, right? What is not known, right, about our underlying MDP is the transition function T and maybe sometimes the reward function R, right? So if we are allowed to look at all possible configurations of transition and reward functions, right, each of them is going to have some likelihood of generating this data, right? So you went from S1 to S2 so many times, S2 to S3 so many times, right? And all those probabilities are basically your transition probabilities, right? Which are unknown, but which T and R, right, which we don't know, has the highest likelihood of generating this data set, right? So let's, you can actually compute it, right? And if you compute it, you'll see that what you should fill for the transition function for any couple of states, right, of going from, let's say, S1 to S1 itself should simply be the empirical frequency that when you left S1, you ended up in S1 divided by the total number of times you left S1, right? So what's happened here is from S1, you had 6 times you were in S1. 2 of those times you came back to S1 and got a reward of 5. 2 of those times you went to S2 and got a reward of 2, and 2 times you went to the terminal state and got a reward of 1. Okay, that's what's actually happened. But if you just write down these empirical frequencies, right, 2 over 6, 2 over 6, 2 over 6, that is the transition function that is most likely to have generated these transitions from S1. Okay, that's actually a mathematical fact. In this case, we have assumed that the rewards are deterministic. So you'll see that every time you go from S1 to S1, you get a 5, etc. But if those are also stochastic, right, then the right thing to do is to average them out for going from any state to any state. Okay, but that MDP, right, that T hat and R hat would be the one that is most likely to have generated this data. Okay, so but why are we talking about this MDP, right? So the question we started out with was, what does batch TD0 converge to, right? And I have now told you, like, from this data set, right, there is this MDP that is most likely to have generated the data set. Now comes the connection, okay? So batch TD0, the estimate that is produced by it, corresponds to the value of pi, okay, the policy that is being followed, B pi, on this maximum likelihood MDP, okay? So MLE is the MDP with the maximum likelihood of generating the data. That's a well-defined MDP, right? And that MDP has a certain value function. Turns out if you run batch TD0, you'll actually converge to that value function, okay? Which is sort of surprising because batch TD0 itself is not doing something like coming up, like constructing a model, right? Constructing the maximum likelihood MDP. Implicitly, it's doing something, right, that it makes so happen that the convergence is to the value function of that MDP. Okay, so this is quite different from what we saw with the Monte Carlo estimators, which were minimizing least squares. Here, what you get is something that is akin to maximum likelihood estimate, the value function under that maximum likelihood estimate. Okay, so if you look at these 3 things together now, right, these 3 estimators, first visit, every visit, and batch TD0 on the same data set, okay, they're going to give you 3 different answers. Okay, just like when we tossed the coin, we had 2 different estimates of P hat. On this data set, if you do first visit, this is going to be your estimate of values of S1, S2, S3. With every visit, this is what it's going to be. With the batch TD0, this is what it's going to be. Okay, so in practice, you might actually not do batch TD0. You'll do TD0 up to some point, right? And so your answer might depend on the value function. But just to have like a clean comparison, let's take the batch TD0 as the answer that's coming out of temporal difference learning. Okay, the same questions remain that we asked last time. Okay, which of these estimates is correct? Which one is more useful? The sort of subtext here, right? The underlying question is the main difference between Monte Carlo and TD0 is you're doing bootstrapping, right? So the other way of asking the same question is it good to bootstrap or is it not? Okay, but as before, there are no definitive answers, right? I cannot really tell you one is better than the other, but I mean, to some extent, right? I think I can give you some guidance over here. I think I'll do it with an example. I mean, I'm doing this ad lib. I didn't really like make a slide for it, but in your mind, right? Think of the following situation. Imagine that you have an MDP with two states, okay, S1 and S2, and the terminal state. So let's say that from S2, you have actually been to S2, let's say 1,000,000 times, okay, and you saw that half the time S2 ends with a reward of 100, and half the time S2 ends with a reward of 0. Okay, so with 50% chance you get 100, with 50% chance you get 0 if you are at S2. And you've seen this millions of times. Okay, you are very confident that this is what's going on at S2. With S1, it is a state that you've not visited, let's say, at all, right? You don't visit it very often. The very first time you visit S1, you go from S1 to S2, let's say with a reward of 1. Okay, and this particular time when you went from S2, you got a reward of 0, let us say. Okay, this is the question confronting you. What are you going to predict as the value of S1? You've only seen one transition, that was from S1 to S2 with a reward of 1. And this particular time from S2, right, you got a reward of 0. So the Monte Carlo way of doing it, right, would say from S1, this is what I have seen. I've seen 1 and 0. And so I'm going to predict 1 as my value of S1. Okay. With TD0, what would you do, right? You're saying, I know S2 has a value of 50, right? Because half the time it is giving me 0, half the time it is giving me 100, right? And the value I'm going to give to S1 is 1 plus 50. Okay, 50 is really the encapsulation of everything I know about S2 so far. It's not only going to look at what happened from S1, which is subject to noise, of course, but it's going to use your knowledge of what happened at S2, and you're going to say that my prediction is 51, right? Because I think 50 happens from S2, 1 has happened from S1, and that has led me to S2. Which of these is correct? Again, neither of these is correct because we've still only seen a finite amount of data from both S1 and S2, right? But it's quite natural to think that in a regime like this, right, where you have lots of data from one state and less data from another state, right? If it is actually true that there is this sort of transition from state to state, it's a good idea to make use of that information, right? So by bootstrapping, you're actually making use of the Markovian structure of the transitions. You're using the fact that you went from a particular state to another state, and you're using that knowledge. With Monte Carlo methods, you're ignoring that information, right? You're not really worried about what state you're visiting in the future. You're just looking at the rewards that you're getting in the future. So that also has some advantages in other contexts. But if you're looking like a small MDP with 5 states and 2 actions, you have a small amount of data, right? You can say that with some confidence that maybe the bootstrapping estimate is going to be the more reliable one to use. Okay, but take that with a grain of salt. Okay, so you will soon encounter situations where bootstrapping in the form that we're doing right now is not really the ideal thing to do. What usually works best is some amount of bootstrapping and some amount of Monte Carlo. Okay, I mean, I haven't told you what that means yet, right? But it would be good if to some extent you trust what you've already learned. To some extent, you don't trust it. Okay, you just trust empirical returns. In fact, you should expect that as you learn more and more, right, you should be trusting your values early on, right? Maybe you trust the Monte Carlo estimate. There's an entire family of algorithms that actually generalizes both TD0 and Monte Carlo methods. Okay, it's called the TD lambda family of methods. And lambda is a parameter that actually allows you to control the amount of bootstrapping. You can actually do this. Okay, when I say a middle path works best, that middle path is composed of a formal way of doing some amount of bootstrapping and doing some amount of Monte Carlo. Okay, so that is coming up next week. Okay, it's the natural follow-up to what we have done now. We've seen the two extremes: only trust empirical returns, fully trust what happens at your next state, bootstrapping. No, do something in between. Okay, and that's TD lambda, and that's what's coming up for you next week. All right. Okay, so the last bit of this lecture, we will take the plunge, right? Make the transition from prediction to control. So again, I think this section is very important from sort of practical standpoint. Okay, the algorithms that you will mostly be using in reinforcement learning are the ones we're going to look at in the next few slides. But conceptually, right, it's just like a small jump from TD0 that we saw in the previous sections. Okay, so what is the basic idea of doing control with temporal difference learning? Remember, the control problem is you want to eventually start taking optimal actions, right? Your job is to take actions, not just come up with a prediction of values, and eventually you want to converge to optimal behavior. Okay, so the only sort of departure that we need in order to do this is, instead of maintaining an estimate of the value function, let us maintain an estimate of the action value function. Okay, instead of v, we're going to have an estimate q. So remember, the q for every state action pair will give you a number. Okay, so the hope is, the direction in which we are going with this is, we want to do something to q so that eventually it converges to q star. In the prediction setting, right, we were given a fixed policy pi. We were trying to get v to converge to v pi. Here we are actually trying to get q to converge to q star. Okay, so it's also different in that sense, because we want to change the actions as we go along and start taking optimal behavior. So the way we will do this is, we will at any point of time follow a policy. So in general, this policy is not a stationary policy. Okay, it has to really react to the data that it is seeing. So the most natural common way of doing this is to have pi t, right, a time step t, being derived from your estimate q hat t. Okay, and the easiest way to do it is to make it epsilon t greedy with respect to q hat. So mostly you're exploiting based on what you have learned, right, based on q hat. With some probability you need to explore, right, because as usual you need to do an infinite amount of exploration before you terminate. Okay, and yeah, just as always, sometimes I might not say this, make sure that epsilon t is such that you'll have an infinite amount of exploration, but also such that in the limit, right, you will be exploiting and not exploring. So what that means is, you can set epsilon t to be again 1 over t or 1 over t plus 1, and make sure that it satisfies the GLIE condition that we need. What we have not mentioned, right, but what is to follow is, how are we going to update q hat, right? We update it exactly according to TD0. So TD0 is the prediction variant of doing it. We'll do a control variant. In fact, we'll do three different control variants on the next slide, which give rise to three different algorithms. But the basic idea is SAR S prime, right? Next state. This gives you some amount of information about the underlying MDP. Okay, and based on this, we will go ahead and update Q hat. Okay, so we're actually going to see three different algorithms. But what really separates these algorithms is just the update rule, right? The way they go from this experience to updating Q hat. Okay, so again, just to make very concrete, we're taking actions according to policy pi t, which might depend on t. Okay, so it's in general a non-stationary policy. So maybe assume that it is epsilon t greedy with respect to qt. And having taken action at, we are going to go to next state st plus 1, get a reward rt, right? So based on this, we will do similarly like what we did with TD0. We're going to do a temporal difference learning update. It's going to look like this in the context of control. So the entry that we are changing is our estimate of ST-AT. Okay, so this is the state action pair that we visited, right? This is what we have the new data for. So we go and change this entry to this plus alpha times a target, right, or a new estimate minus our old estimate. Exactly the same thing as, okay, this should be a superscript, I think, okay, not a subscript, but never mind. So we go ahead and do the same sort of update. The only thing that is unspecified yet is what really is target, right? So target must have the semantics of like a new estimate of the expected long-term reward of STAT, right? So again, we're going to do bootstrapping, but we can actually do this in many different ways. Okay, so what we've listed here are three fairly common ways of filling that blank, right? Of what is the target that we're going to put in over here as a function of S, A, R, and S prime. So maybe the most popular of algorithms for doing updates is Q-learning. Okay, Q-learning is an old algorithm, and in Q-learning, this target is defined to be reward plus gamma times max over all actions of our current estimate of Q of ST plus 1, T plus 1 action. Okay, so we have currently Q hat, right? And in our table, we'll actually have entries for Q hat of ST plus 1 and every possible action. Okay, now we ask, once we get to ST plus 1, what is the best that we can do? I mean, imagine that actually we have converged, right? And Q hat actually has become Q star or something like that. What would you be doing, right? The thing that you would be doing is to take the optimal action from there, right? So, of course, at any point of time, we can't guarantee that Q hat will be Q star. It won't, right? After a finite number of steps. But we'll still conceptually behave as though it is, and say that what we can get from ST plus 1 is what we currently have as Q hat of ST plus 1A, and let's pick the action that gives us the maximum value, acting as though we're going to take that action. So in reality, you might not take this action, right? In reality, when you go to ST plus 1, you'll act according to pi t plus 1, which might give you this action to take or not this action to take. It doesn't matter. For ST, the update is according to max of Q hat T of ST plus 1A. Okay, plus reward, of course. Okay, that's Q learning. There's, of course, other ways of doing it. SARSA is maybe the more conceptually easier algorithm to describe. So the action that is taken in this update, right, for SARSA is different from the maximizing action. See, when you get to ST plus 1, you will actually pick an action AT plus 1, right? So once you've decided which action that's going to be, you go back and update QT, right? Make it QT plus 1. And the target that you're going to set is simply R plus gamma times Q hat of ST plus 1, AT plus 1, the action that you ended up taking. So again, from ST plus 1, AT plus 1, you'll get a next state and a next reward. Again, you'll have to wait for deciding which action you're going to take after that, right? And then come back and do the update. So there is a slight difference in timing between Q-learning and SARSA in that as soon as you reach next state, right, with Q-learning you can make an update. For SARSA, you have to decide which action you're going to take next, right, and then do the learning update. But otherwise, there's not much of a difference. The reason it's called SARSA is for the reason that you're looking at state, action, reward, next state, as well as next action, right? It's SARSA. And all those 5 things came together and the algorithm is called SARSA, okay? The third variant is called expected SARSA, which is conceptually similar to SARSA, but it's sort of just different in one respect. Okay, so with SARSA, right, when you reached ST plus 1, you decided to take AT plus 1, and therefore you did this update. With expected SARSA, sort of semantically, you're doing the same thing, right? But you're not doing it based on the AT plus 1 that you took. You're sort of doing an average over all possible AT plus 1s that you can take. Okay, so instead of doing an update using a sample, you're doing it based on an expectation. Precisely what are you doing? You're saying once I reach ST plus 1, well, you might actually take actions according to pi t plus 1 at that stage, right? But let's just take pi t and look at like an expected value of the Q's weighted by the probability of you taking a particular action. So look at every action and ask what is the Q value of that action, I mean, that I think it to be right now. That's why you have hat Q T. The weight corresponding to that is the probability with which you're going to pick that action. Okay, so this is like a weighted expectation of your of the what you think is the Q value, right? That you're going to, or rather the value, right? Once you reach st plus 1 by following the current policy. All right. So again, expected sarsa is similar to Q learning in that as soon as you reach st plus 1, you can do the expected sarsa update. Okay, and once you do the update, you can decide which action to take, because you're doing sum over all actions using pi t. Okay, but notice that you're not doing any maximizing over actions over here. You're still the concept is still that you're doing an action assuming that you're going to be following your current policy at st plus 1. Okay, so these are three different variants of doing updates. There are many others, by the way. Okay, but you can see that all three are full bootstrapping, right? Like TD0, you're, as soon as you go to st plus 1, right, you're using your current knowledge at Q to decide what the target, right, or what the new estimate is going to be. That minus old estimate, right, multiplied by alpha plus the old one gives you the new estimate. Okay, so although these three variants are sort of subtle in their differences, they do actually have difference in properties, right, convergence and things like that. So one technical term that you need to be familiar with is what is called off policy versus on policy. Okay, so Q learning, the update that is made in Q learning is called an off policy update. So why is it called an off policy update? It's because the update you're making, right, the target that you're setting for yourself depends on an action which might not be the action that you actually take. Okay, so you're taking your, for example, you go to st plus 1, maybe you'll take an epsilon greedy action that will be quite different from the action that is maximizing Q hat at this point of time, right? So although you might behave in a certain way, right, you are making updates each time, assuming that when you reach st plus 1, you'll take an optimal action. Okay, and in that sense, it is off policy. Sarsa is clearly on policy, right? You're actually doing an update based on the action you ended up taking. Expected sarsa is not, I mean, on policy in the same sense, right? You are not doing an update based on the action you took, but sort of imagining the action that you will take. Okay, probabilistically, you are invoking your policy, right, and seeing what action you will take and doing an update based on that. So expected sarsa is also on policy in that sense. Okay, and turns out, okay, we will not do these proofs, that all three of these methods, okay, will take Q hat, make it converge to Q star, so long as the policy that you're following, right, pi t is epsilon t greedy with respect to Q hat. Okay, so most of the time act greedily, with some of the time do exploration, just to make sure that every state action pair is visited. Okay, and of course you have to set epsilon accordingly. But you do it right, all three of these methods will lead to convergence to Q star. Okay, but the difference between off policy and on policy becomes clear if we consider a slightly different way of taking actions. So imagine that we are following a fixed policy pi. Okay, a policy that in general can be non-stationary, but assume that we are actually fixing our policy and then doing these three different updates. So if the policy is one that actually takes every state action pair an infinite number of times, which means it has to be a stochastic policy, which is giving some probability of taking every action from every state, right? Then what Q learning converges to is different from what sarsa and expected sarsa converge to. Okay, and this is because Q learning is off policy in its updating, right? It's updating with respect to the max. Sarsa and expected sarsa are on policy. Because they're on policy, sarsa and expected sarsa will actually converge to Q pi. Okay, the value function of the action value function of the policy that we're following. Q learning, on the other hand, will actually still converge to Q star. Okay, so eventually it will figure out actual Q values, right, that are optimal, okay, because of the nature of its update. And it's visiting every state action pair an infinite number of times. So it will actually still converge to Q star. Of course, it won't converge to Q star if pi is not visiting every state action pair infinitely often, right? I mean, there's no guarantee that it will. But given sort of enough information, Q learning will converge to Q star. The important thing is if pi is actually greedy with respect to Q, epsilon greedy with respect to Q, and epsilon is annealed properly, and all three of these methods do indeed converge to Q star. Because you're being epsilon t greedy with respect to that, you'll also be taking optimal actions in the limit. So remember, right, when we had formulated the control problem in reinforcement learning, the question was, can we eventually realize behavior that's taking the fraction of optimal actions that you take, right, is tending to 1. So that answer is in the affirmative, yes, for all 3 of these methods. So let's step back a little bit and just review what we have done in this week's lecture, because it's a sort of important set of concepts. The main one, right, amongst them being temporal difference learning. Okay, that's the thread that we have introduced today, and that really runs through a lot of reinforcement learning. So TD learning is a way of doing online learning. Okay, so the idea is you're doing a very simple, computationally cheap update, but you're doing it at every time step. Okay, you go from S to S prime. You've gotten a little bit of information with which you go and update your current knowledge, which might be an estimate of V or Q, depending on whether you're doing prediction or control. And you can see that you can do it both for prediction and control. We have sort of argued that you'll converge to V pi or Q star, right, if you do this properly. Important thing to notice, okay, the main difference between the algorithm we gave for control last week, right, and the one we have seen today are, the one we saw last week was model based. Okay, we actually constructed a model which meant it had S squared A parameters, right, with S states and A actions. But think about Q learning SARSA, expected SARSA. What is the size of the memory that we need? It is the size of a Q table, right? We have like Q at any point of time, and so that is just the number of states times the number of actions. So this is a significant result in that, in spite of just having S times A memory, we have a process that in the limit will converge to optimal behavior. Okay, and this is quite advantageous also when we look at more generic formulations. When, for example, you have a very large number of states, right? You're actually probably better off sometimes doing model-free RL as opposed to model-based RL. This is also something that we'll encounter in the next few classes. The crux of temporal difference learning, or rather TD0, right, is bootstrapping. So that is another concept that we introduced today, and the idea is you are using the Markov property. Okay, so what you already know about the MDP, right, in your next state you are using to change your update for the current state. Okay, this is something very, very defining about temporal difference learning and what we've seen today. And this is something that Monte Carlo methods sort of sidestep, right? They just look at the sum of the rewards. They don't look at the value estimate that you currently have. So as I already hinted to you, often the right thing to do is to do both of this to some extent. Bootstrap to some extent, don't bootstrap to some extent. Trust your empirical returns to some extent. And that is precisely what you can do using the TD lambda family of algorithms. So TD lambda is for prediction. You can also apply the same idea to control. The idea of lambda is it's a parameter that is between 0 and 1. And the reason, by the way, that we've been calling our algorithm TD0, so maybe I left you wondering for a long time why it was TD0. It's TD0 because it's TD lambda. Okay, that tells you that TD lambda is something more general than TD0, right? So you can actually run TD lambda with any lambda between 0 and 1. As you make lambda larger and larger, you're doing more and more in the style of Monte Carlo, right? In fact, TD lambda with lambda equal to 1, right, which is TD1, is basically every visit Monte Carlo. Okay, although we've been calling it every visit Monte Carlo, when we actually describe TD lambda in the next class and we set lambda equal to 1, right, you'll see that it's basically doing the same thing as every visit Monte Carlo. And lambda is this parameter, right? You can vary it between 0 and 1 to vary the amount of bootstrapping. Okay, and this is coming up next week. So again, we're getting into the thick of things. Okay, starting to look at concepts that are uniquely reinforcement learning, and we'll continue with this. We'll do TD lambda, which is again a very central topic next week, and we'll also start considering more practical considerations like what to do when you have a very large number of states. Okay, all right. So stay safe and take care. I'll see you next week.